Hello friend, welcome to my channel. So today I am going to discuss about the revision of spectroscopy of organic chemistry. So in this revisions basically I am going to talk about some instrumental technique which is very important in research fields and others things like these instrumental techniques applications is very important for our experimental based data, means collect the information about the any compounds. Okay, so before I start, so I request to, if you are new in this channel, so please like and subscribe and share with your friends and click the bell icon, okay, for get the easily notification. Okay, so now it starts. So spectroscopy, and this is very important. There are a lot of questions have been asked in several exams, so it is very important topics. So spectroscopy. So it is basically theoretical as well as mathematical. Okay, so don't worry, and it's very easy also. So it's spectroscopy. So what is spectroscopy? Spectroscopy basically it is a technique which determine the information about structures and through this technique we study the interaction of matters and electromagnetic radiation. Okay, and actually from this technique measure the amount of light absorbed by the any compounds as a function of wavelengths. Okay, so it is a basically it is a technique which determine the structures. Okay, structure determination technique है. It is a structure determination technique, and what will actually happen? Actually, the interaction of matter means interaction of matter with electromagnetic radiation. Electromagnetic radiation is measure the or determine the structures of any compounds. Okay, and from this actually measure the amount of light absorbed by the any compounds. So actually measure the amount of light absorbed by the compound as a function of wavelength lambda. Okay, wavelength of light. So here basically we measure the amounts of light, how much your compounds amount light absorbed, and this data will depend with respect to wavelengths. Okay, so here basically we focus three techniques: UV visual, IR and NMR. Okay, these techniques are very important, and through this technique your way to determine the structure is become very easier. Okay, so what will happen in this UV visual spectroscopy? It is basically electronic. In this, through this technique, electronic transition happen. Okay, and through this vibration of bond. Okay, and through this basically the nuclear magnetic transitions happen. Nuclear magnetic transition happen. So these are the basic terms about these three techniques. So I will take one by one. I will give the introduction about all these techniques. So first I will go to the UV visual spectroscopy. Okay, so from this technique basically the actually first I will write the range. This ultraviolet means higher energy means lower wavelength. So the range will for ultraviolet is from 200 to 400 nanometer, and this is visible. Lower energy but higher wavelength means 400 to 800 nanometer. So this is the range, different range for different light source. Okay, so so this is actually best, as earlier told here, measure the amount of lights absorbed by the compound as a function of wavelength. So if you write the relations, lambda is equal to c by mu, where c is the speed of light and mu is the frequency of radiation. Okay, radiation frequency. This is radiation frequency. As all you familiar, speed of light 3 into 10 to the power 8 meter centimeter inverse. Okay, centimeters meters per second, and we can also write here E is equal to h nu, and nu is equal to, we put nu here, c by lambda, so c by lambda. Okay, so this is, you will get relation E barabar hc upon lambda, and again we write hc mu, this is wave number. Okay, so 1 upon lambda is equal to wave number. So this is energy of radiation, this is Planck constant. Okay, and frequency of radiation, as I told, in hertz, RCPS, and lambda is wavelengths. Okay, this is wavelengths. So this is the very basic formula you people has known. So now we move to the this absorption spectroscopy technique, because I am talking about UV visual. So this, inside this UV visual, we will discuss absorption spectroscopy. So I will give in short way to explain the technique. So here you have radiation source, your light is radiated from this is monochromatic radiation incident, this sample, this is your sample, and this is transmitted light. Okay, so here your sample, this is your sample, absorbed some light and electromagnetic radiation light, and this light we can't measure. Okay, this is can't measure because this light is not absorbed by this sample. Okay, and here your detector. So only we measure this absorption, how much absorbed your sample lights. Okay, so this is technique we measure the absorptions. Okay, so now we move to the about spectra. Okay, so there are some spectra like inside this we get the absorption extra through electronic transition, and as I told you. Okay, and rotational energy, there are several things inside this. So now we discuss about the which is very important about inside this UV visual spectroscopy. So basically we will discuss the Lambert law, because a very big role for this absorption spectroscopy. So actually two empirical laws formulated about the absorption intensity. First, Lambert law, Lambert's law. What Lambert law tells? It tells about the fraction of incident light, means fraction of your monochromatic incident light radiation absorbed by the homogeneous samples, okay, in the medium is independent of the intensity of incident light. Means this your sample is independent of the intensity of incident light, so it is totally independent of this intensity of incident light. So this is transmitted, sorry, this is I is transmitted, this is I0 is incident intensity. So here this last is the fraction of incident monochromatic radiation absorbed by the homogeneous medium is independent of the of the intensity of incident radiation. Okay, but Beer's law says the what Beer law stated. So Beer law states that the absorption of monochromatic radiation by this homogeneous samples is proportional to numbers of absorbing molecules. So here it states that this absorption of monochromatic radiation this monochromatic radiation is proportional to the numbers of absorbing molecules. Okay, so it depends on the numbers of absorbing molecules. So absorption at the particular wavelength is defined as, because only this sample absorbed at a single wavelength light, not difference. So we define a equation for a particular wavelength, as you all already familiar with this. Absorption equal to log of I upon I0. Okay, so this is the equation where this is absorption and this is the transmitted intensity, this is incident light intensity. Okay, so here actually two beams are using. So this is for reference radiation and this is for your beam coming out from the sample cells. Okay, so here relations comes out, absorption is proportional to concentration as well as your path lengths. Okay, so if combine this proportionality you will get the C into L, and removing this proportionality you will get the epsilon C into L. So this is your relations of this. Okay, combines Beer's Lambert's law. Okay, so this is the extinction coefficient, or molar absorptivity, and C is concentration, and L is the cell length in centimeters. Okay, right. So up to here you all are familiar already. Okay, so now move to the other things. Other things means one most important formula also you can keep in your minds. Absorption is equal to log of, this is transmission percentage 100%, so T, and as you can write 2 minus log of T. Okay, you can directly put here T in percentage. Okay, so this is also formula which is very important, right? So here you have to follow some energy transition like sigma star and pi star and this non-bonding, this is pi, this is sigma. Okay, so how much required energy to get different transition? Okay, if your simple transition happen from here to here, means from here sigma to sigma star, so you have to require energy for this greater than 175 kilocalorie. Okay, so this much energy you have to require for this much transition. Okay, delta E, sigma to sigma star. So, and for pi to pi star, sorry, pi to pi star, for this transition we have to require delta energy, delta E, some less than 170 kilocalorie, this much energy for this transition. And for this transition, pi to sigma star, and for this transition pi to sigma star, you have to require energy less than 150 kilocalorie. Okay, and for non-bonding to pi star, this is your non-bonding to pi star, require very less energy, 105 kilocalorie. So from this transition you can get the idea about this is the big gap between the sigma to sigma star transition. That's why you have to require this much energy, and for this pi to pi star you have this much, and similarly lowest non-bonding to pi star require this much energy. So usually you can understand from this energy gap, okay, of this sigma pi star. So now we'll discuss about the lambda max. So lambda max, how wavelength is depends on different molecules. Like if I am saying benzene has 256 nanometer wavelength, so how this value comes out? Okay, so for what reasons different molecules have different lambda max value. Okay, so now we'll discuss about this, okay, because this is very important. So we discuss the designation of absorption band. this is very important. Okay, so this is also under UV visual absorption band, may be designed by the types of electronic transition from which they originate. Sigma to sigma star transition band or pi to pi star transition band. Okay, so first I will discuss K band. It is nothing but this band originated from pi to pi star transition. Okay, any compound having pi conjugation. Okay, pi conjugated system, if any molecule having present, then this transition will take place. Okay, so if we take the examples, see the example. Let's 1,3 butadiene. So for this lambda max is 217, okay, nanometer, and there are several molecules. Okay, acrolein, here lambda max is 210 nanometers. So there are several. Second, discuss about R band. So this is here we actually consider the N to pi star transition, non-bonded to pi star transition. So it is a single chromophic group like carbonyl, nitro group. Here we basically consider nitro, carbonyl. Okay, carbonyl group. So here basically consider this group. Okay, so these band also called the forbidden bands. We can say the forbidden band. Okay, and R band are less intense with epsilon max value below 100. So if we see acetaldehydes, example acetaldehyde, so lambda max value is 290 nanometer, and acetone, if you take acetone, so lambda max value is 279 nanometer. So you have to remember this value because this value is very important. So now if you see talk about third, B band. So B bands, here we discuss about actually this band also is originated from pi to pi star transition in aromatic and heteroaromatic. So this is telling about aromatic, means pi to pi star transition, which is in aromatic or heteroaromatic. Okay, so here is the example for hetero and aromatic. Okay, so if we see in benzene lambda value is 250 nanometers, and similarly toluene lambda value is 262 nanometer. Okay, similarly naphthalene lambda value is 312, like that, etc. So okay, right, hopefully you guys understood. So this is data. Basically you have to remind, this is not sorted, this is the only the one option only. You have to remind all these data. Okay, once you 1 2 3 times you remind, then after automatically you will keep in your mind. Okay, during solving the problem. So now we will discuss the terminology used in UV spectroscopy. Okay, so which types of species increase the lambda max or decrease the lambda max. Okay, so that terminology I will discuss. So terminology so first chromophore. So chromophore so here this actually the covalent unsaturated group responds for all this absorption in the UV visual. Okay, so here basically we consider the covalent unsaturated. Okay, so unsaturated means carbon, double bond carbon, triple bond, C double bond, C triple bond, and etc, and double bond, and etc. So here the carbonyl group is a chromophore. Okay, synthesis absorbs UV region in around 280 nanometer. So molar extinction coefficient is about the 15. So okay, so chromophore which contain sigma or pi electrons like this is here sigma and pi electrons is contains here. So these are the chromophore. Okay, like see it, this like your benzene, this. Okay, so these chromophore under to pi star transition. Okay, right. So other chromophores, other types chromophore where the contain means pi and non-bonding electrons. Okay, so examples, if you take example, this is having lone pairs non-bonding electrons, and if you see this and this, okay, etc. So basically this undergo chromophore. First one undergo pi to pi star, and second undergo N to pi star transition. Okay, this one go under this. So this is all about the chromophore. So auxochrome, now we'll discuss the second terminology. This one first, terminology second. Auxochrome. So auxochrome when attached to a given chromophore usually cause shift of absorption band to longer wavelengths, which simultaneously increase the intensity of absorption band, is called auxochrome. Okay, so here basically when attached any chromophore group here, when the cause any shift of absorption band with longer wavelength, then increase the intensity of absorption band, is called the auxochrome. So here some common auxochrome groups like this: alcohol, like this, okay, and etc. This. So this is basically your chromophore. This group increase the wavelength of chromophore, okay, because these are the basically electron withdrawing, electron donating group, okay, that's why they increase the absorptions bands through any shift longer wavelengths, okay. So here these are used for usually use the shift of absorption band, shift of absorption towards higher wavelength. Okay, right. So this is the your auxochromes, okay. So auxochrome basically increase the lambda max as well as epsilon max value also through resonance or hyperconjugation, okay. So this is the auxochrome, right. So now third terminology is bathochromic shift or rate shift. So bathochromic shift is basically a shift of absorption maxima to a longer wavelength is called the bathochromic. So here we'll when a shift of absorption maxima to a longer wavelength, okay, longer wavelength is called the bathochromic shift, okay, or red shift, we can say the red shift. So here any factor which stabilize the molecule cause the bathochromic shift, okay. So you can write also other form, any factor which the terminology. These are the three terminology which affect the your lambda max. Okay, so now we have to write some note points. Note points is there are some different effect which affect the lambda max value, like solvent effects, and there are several effects. Okay, and there are several factor which affecting the lambda max value, like resonance effects, and hyperconjugation effects, hydrogen bonding effects, okay, steric effects, and okay, there are a lot of effects. Okay, you should also know about these effects which affect the your lambda max value. Okay, so now we will discuss the second thing, infrared spectroscopy. So before going to infrared spectroscopy, I will give some notes points. Okay, notes number one. When a conjugation increase in your system, then increase the conjugation in a system, then transition will increase, and lambda max also increase. Okay, as conjugation increase means your homo-LUMO gap is decrease. Similarly, homo-LUMO gap decrease. Okay, this point number one. So, and point number two. So if any electron releasing group is present in your chromophore, then lambda max will also increase. Okay, and if electron withdrawing group is present, then there will be small change will happen in lambda max. So this is the very important. Lambda max when increase when the electron releasing group is present. Okay, right. So this is the all about usual absorption spectroscopy. Right, so now I'm going second technique, infrared infrared spectroscopy. This technique is also very important exam point of view. Okay, through these techniques we actually get the information about the structural details of organic compounds, and actually here the identification of large numbers of organic functional groups because they show the specific characterization, absorption, infrared region. And this infrared spectroscopy absorbs in vibration of molecular bonds. Okay, so this technique observes in observes the vibration of molecular bond. Okay, and it is used basically to infer the nature of bonding and function group, which function means which types of functional group is present. So it is used basically the determine the nature of binding and functional group. It tells about the nature of bonding as well as functional group, which functional group is present. Okay, and this technique is only single technique which allows for direct identification of functional group. Okay, right. So this is the introduction about the infrared spectroscopy. So now we will talk about which range here the, and one thing I will add one points. So only those band absorb IR radiation which have dipole moment, means only dipole means only okay, we can write another way, means this point the IR radiation absorbed only and IR radiation absorb only those molecules which having dipole moments. If the dipole moment is not present in the molecule, means that molecule will not absorb this infrared lights. Okay, right. So basically polar molecule, dipolar means polar molecule is good for this technique. Okay, non-polar is not good. Okay, right. So now we will write the absorption range, which range this light absorbs. So it absorbs from 303 to 4000 centimeter inverse. Okay, this is the unit of this absorption light. So now actually this is the middle infrared region, and there are three regions of this infrared: near infrared and far infrared. So I will give the information about also near infrared. So near infrared is a region in 12,820 centimeter inverse to 3,333 centimeters inverse. And far infrared region is 303 centimeter to 33 centimeters. So this is far infrared, this is near infrared region. Okay, and this is your middle infrared regions. So middle infrared region has energies ranges from 10 to 1 kilocalorie per moles. Okay, so this theme basically infrared is basically based on the frequency. So frequency, how to correlate frequency? Basically frequency we can correlate with through Hooke's law, and one important formula here we write. Actually percentage transmissions is equal to I upon I0 into 100. Okay, and I as I told earlier, absorption is inversely proportional to transmission, and okay, and this formula 2 minus log of t. Okay, so you have to, these are the very important formula you have to revise. Okay, so as I told, greater the polarity bond, higher will the intensity. Okay, so here your molecule should be polar. Okay, then intensity will be the higher. Okay, so now we will talk about the means one other 2 points I will also tell you: IR active and IR inactive. So vibration of band with non-zero dipole moment generally tells about the IR active, and IR inactive when the no absorption of energy means there is no change in dipole moments. Okay, so when dipole moment is equal to 0, then IR inactive. When it does not 0, okay, then active, IR active. Okay, so these are the points about infrared spectroscopy. Okay, so there are some examples which shows the IR active and inactive. So I will give some examples. So this is the inactive, IR inactive, because net dipole moment is 0, and for this is active. Okay, IR active. So here direction of this vector quantity is same side. Okay, that's why the actually this is unsymmetric stretching and this is actually symmetric stretching. That's why the this is inactive, this is active. This is unsymmetric stretching, and stretching mu max value is for this is 50 centimeters, and for this okay. So like that we see other example also. This is this, so this is also unsymmetric, so this is also active, this is also active, and last this is also active. Okay, so these are the examples, IR active and inactive. Okay, this video is going to very lengthy, so now I will stop here. I will give next means material in next video. Okay, so okay, bye bye, thank you.